Okay, the recording is on. So hello, everyone. And after a 5-month break, welcome to another hot electronic seminar talk. It's yet another season wherein the NBC decided not to offer me the Tonight Show. So I'm back to hosting Hottest, which is great still. Since we're starting a new season, I'm just going to give you a short reminder of what we're into. So there will be a 1-hour talk followed by up to 30 minutes of discussion. During the talk, we ask that you keep your cameras on. It's nice for the speaker to see some faces rather than just black screens, and that you keep your mics off so that there's no background noise. If you, at some point in the talk, want to ask a question, just unmute your microphone and ask the question. And that's pretty much it. Andrej told me that he'll be monitoring the chat as well. So you can also write your question in the chat, and he will try to address it. And I think that's all I have to say in terms of the organizational stuff. We're recording. Okay, now I'm happy to introduce Andrej Bauer, who will give the inaugural hottest of the season, and his title today is A General Definition of Dependent Type Theories.
Okay, I hope I am being heard here. Can everybody hear me?
Yes.
Yeah, okay. And I am sharing something that looks like a slide.
Yes.
Okay, so just to let you know, in my office, there are also my students, Anya and Philip. And let's go back to sharing there. I should be back to sharing about now. Okay. Okay, so regarding the questions in the chat, I think two of my co-authors are both here, they might field some side questions in the chat if you have a small question. So we'll see how it goes. But if you have any kind of a question, I would really prefer that you interrupt me than wait 40 minutes and then ask afterwards. Just go ahead and ask in some way by unmuting yourself or by using the chat. So first of all, I'd like to thank Chris for inviting me and also apologize that I actually was supposed to speak in the spring, and then I bailed on him because I had a very good reason, which was I had to go to Bosnia to a wedding. So that was fun. Okay, the work I'm presenting here is joint work with Philip Haselwarter, who's a PhD student here in Ljubljana, and you just saw him behind me, and Peter Lumsden, who is also present at this talk. At least the left half of his face seems to be present. The question that we want to answer today, or that we have been working on for quite a while now, is what are type theories? So I think this is an important question. In a way, it was asked by Vladimir Voevodsky many times, and he wasn't happy with existing answers and so on. And that's how I got to think about it, by eventually taking Vladimir seriously. There are many examples of type theories, of course. There are Martin-Löf type theories, calculus of inductive constructions, computational type theory, cubical type theory, cohesive type theory. You can name any number of type theories and variations of type theories. And we all know a type theory when we see one, but can we define what type theories are? So that's what I'm interested in. Now, you might wonder why we need such a definition. So, this is akin to say something like, what is a geometry, right? For a more classical subject like geometry, it certainly helps to think about the question, what is a geometry? Because obviously having a good definition would have many benefits. But you also see that for an open-ended concept such as geometry or type theory actually, or space, there isn't going to be a single definition that will make everybody happy forever. So what we should shoot for is a general enough definition so that it starts to have a life on its own that encompasses a large enough family of type theories. But maybe we also, because this is just like our first attempt, we don't want to do it too widely. We want to be able to control the definition. Once we have a definition, what can you do with it? Well, okay, so first of all, it would give us the ability to have a general meta-theory of type theories. For instance, when people define particular type theories, they always go down the same route. For instance, they prove some sort of substitution lemma or substitution admissibility or elimination and other meta-theorems. And everybody keeps doing them, or they just say, oh yeah, the meta-theorem is going to hold. We have done this 10 times for other type theories. But that's not really how mathematics should be done. I mean, we should have a proper definition and then prove these meta-theorems once and for all, for instance. So that would be a decent meta-theory of type theories would be one benefit. Another benefit would be that this way you could also have a general semantic account of type theories that's better than just, oh, the semantics of type theories is something like categories with attributes or some such. And then you don't really say what is the syntactic side. You see, it seems like people have given many good answers to what is the semantics, what are the possible semantics of type theories. But what's sitting on the other side to be, we want to be precise about that. It shouldn't be just 10 examples. Another reason why we would want such a definition is if we wanted to implement a proof assistant with user-definable type theories. So then we would need to understand precisely what is the scope of such user-definable type theories. And that's something that actually we've been working on in the Andromeda proof assistant, but it's not quite ready yet. So I'm not going to talk about it today. Okay, so before we even give an answer, we should consider what are some possible approaches. How could one even attack this question of what is a dependent type theory? So what kind of an answer would we want? Well, so for instance, the answer is going to involve describing a formal system, right? So the answer is going to be of this form. It's going to say, let me switch to black here. It's going to say something like, oh my God. Okay, here we go. A type theory or a dependent type theory is a formal system of some sort. And then there need to be conditions about this formal system, and they're going to what is going to be mentioned in this definition when this formal system is described. Well, okay, so there's going to be syntax of expressions and types in some shape or form. And there may be other syntactic entities involved. One aspect of the syntax is always going to be binding of variables, because we're talking about dependent type theories. So there needs to be binding. How are bound variables treated and so on, and dependencies. Keeping track of which thing is dependent of which thing. Then there is going to be something about judgments and judgment forms. And then a notion of derivation has to be provided. What is a derivation and so on. And so these are all syntactic notions. That's what I'm talking about. So I'm not talking about semantics. And you can shoot here for different levels of generality, and it's easy to be too general. For instance, you just say a type theory is any deductive system. Now that's silly, because obviously there are things which are deductive systems but are not type theories. But it's also easy to be too specific. For instance, you could say, we're only going to consider type theories which have pi's and sigmas. And that's not the kind of specific thing we want. We want to be a little more general than that, so that one gets to introduce pi's and sigmas if one wants to, but you don't have to. So we don't want to rely on anything, any specifics like that. I would like to also point out, let's compare this to the usual treatments in classical logic. So if you open a book in classical logic from 1960, they're going to talk about first order logic. And so what am I doing? Like if I try to compare myself to what they are doing, what am I doing? So what we're doing here is quite a bit more general. We're not asking, the analogous question that we're asking is not what is first order logic. We're asking what are logics in general. So that's the sort of question we're asking here. So we should expect this to be sort of very open-ended and maybe also a bit complicated. Now, how do we attack the question? So what are some possible methods for answering this? In particular, what I have in mind here is methods for dealing with this sort of syntax. Or more generally with such formalisms. So you could do, you could try and say, okay, I'm going to do this old style. I'm going to use concrete syntax. So in concrete syntax, your basic entities would be actual strings of characters, right? So you'd say, I consider strings or sequences of symbols, words. And then you do things like when is a word a well-formed formula and so on, and that's obsolete. Or let's say this part of syntax, this level of syntax is well understood, it's been done to death, that's not the right level. So you could move yourself a little bit up and you say, okay, we're going to go to abstract syntax. So our basic entities, like expressions and types, they're going to be well-founded trees. So abstract syntax trees. And that's reasonable, that's more reasonable. It's still going to be quite detailed and it's going to have to deal with lots of details. And that this is the thing we're going to do, okay? So this is where we are. And so that means we are going to talk about things like expressions and types and how they're formed inductively as well-founded trees. In what sense does this say well-founded? It doesn't really say well-founded. Well, F-O, okay? You could try to go beyond that and have something that I don't really know what to call this, but I've heard it called intrinsic approach. So I'm writing syntax here, although I really mean something slightly wider. Intrinsic syntax would mean that the entire thing is, so all the syntactic entities are actually objects of some meta theory, of some meta level formal system. The two obvious choices being here, so something like a logical framework, or the Nottingham approach using type theory and maybe quotient inductive types. So there may be an ambient type theory. Now, this is going to have lots of benefits because you will get things like binding for free. You will just import it from meta level, and a bunch of things will just work out, and it will feel like it's a very elegant way of doing things. I agree with all of that, and we did think quite a bit about whether we can pull this kind of thing. How can we pull this kind of thing off? And the conclusion that I've come to is this: somebody has to do this nasty thing at this level so that we can then actually understand what are the exact conditions that we want on a well-behaved type theory, so that then we can try to express them using fancy technology down here. I think it's really hard to try to get a very general definition. So for instance, it's easy to give a definition that is too specific or not specific enough. To give you an example from kids, it's easy to, well, easy, it's not, you know, it has been defined. I don't want to minimize the efforts that were put into that, but the quotient inductive types have been used to define a specific type theory, like, you know, intentional type theory with pi's and sigmas and identity types in one universe. And that has worked. That's one specific example. But then if you ask what is the type of all such things, then you're left without an answer, because just saying it's any old quotient inductive type is obviously too general. But then you have to answer, well, okay, but what are the exact conditions? And at least I don't see how to get them until some sort of a very detailed analysis is performed, maybe at a lower level where we can build things up and we get to consider all the things that we don't want to. So you see, maybe this is a point worth making. These three approaches are, each next approach is more abstract. So here you deal with stupid things like words are finite sequences of symbols, and then parentheses have to be well balanced and blah, 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 blah. And it's all very annoying. And what you're doing is you're carving out the thing you want out of some chaos of words and symbols. So the abstract syntax approach is slightly better. Here, expressions are well-founded trees, so you don't have to worry about things like balancing parentheses, but you still have to worry about the fact that maybe you can write nonsensical inference rules. And now you have this chaos of possible nonsensical inference rules and possible nonsensical formal systems, and you have to carve out the stuff that you're interested in. Whereas this last bit here is most abstract, and also is, you know, the chaos that is surrounding you that you need to cut down on is now even more well behaved. For instance, you would imagine that in this approach, you wouldn't have to separate things like expressions and types from their corresponding inference rules. It would all be neatly packaged so that once you write down the inference rules, you already know what the syntax is and things like that. A lot of things would come for free. You wouldn't have to deal with, maybe you don't have to deal with congruence rules, maybe you don't have to deal with substitution at all, whereas you have to do all of that at that level. So eventually we want to go down this road and land somewhere where we have a nice abstract definition of what type theory is, but I just don't know how to get there, and I'm hoping that this is a stepping stone on the way there. I should also say that there is quite a bit of related work, because I mean, this is, and I think this is an interest. Other people seem to think that this is an interesting and relevant question. I'm probably not aware of everybody. I know that Guillaume Bernery in Stockholm has been working on this, and then what I call the Nottingham group. So that's Torsten Altenkirch, Paolo Capriotti, Ambrose Capozzi, who is not in Nottingham anymore, and then his co-workers in Budapest, Andrej Kovac, Nikolai Kraus, wherever he is, Jakob van Roemer. So that's the Nottingham group. And there is an interesting recent paper by Taichi Uemura. But I'm not going to, unfortunately, I don't think I have neither the time nor sufficient knowledge to comment on these other approaches, but I think we're all striving for the same general definition here. Okay, so what can one expect of such a definition? So we've been writing this paper forever, which eventually is going to appear, but the steps would go somewhat like this. What are the steps of our definition? Okay, so first, you would have some mathematical preliminaries. And I would hope that this audience is fairly familiar with them, like what is a derivation, what is an inductive definition, things like that. So I'm not going to comment a lot about that. Then there will be quite a bit of stuff about syntax. And then there would be something about So the way we're going to do this is, so there's something about syntax of expressions and types and so on. And then we're going to set up type theories by starting with a very permissive definition, which is obviously too wide. And we call this kind of definition raw type theories. And to be quite precise, because the syntactic stuff that we're going to talk about here, this is also quite permissive and allows there to be things that we don't actually want in the end result. We're going to call this one raw syntax. Now, once you have a notion of type theory, like at least some semblance of type theories, you can start to analyze what makes, for instance, what makes an inference rule good? Because if you show an inference rule to some, like you pick a person in Sweden, you show them an inference rule, they will be able to say, it's a good inference rule, it's a bad inference rule. So then you try to figure out what are these conditions, and maybe you come up with some conditions. And so we are going to stratify them into two steps. The first one is acceptable type theories. So this is going to put restrictions on rules and the type theory of the kind, you did not forget to give me rules for this particular symbol. Like if you claim that your type theory has a symbol called pi, then presumably there should be some inference rule for pi, and maybe there should be just one rule for pi. And that's the sort of thing that you should enforce, and so that's the acceptability. Now, the thing that this level 4, this stage, doesn't prevent is cyclic definitions or infinite descent. So you could, in principle, have a rule which is only well-formed because in order to show that the rule is well-formed, you have to, for instance, you have to appeal to the rule itself. Or you have a type symbol which sort of speaks about itself in the premises in some bad way. So that's the sort of thing you don't want. So the last step is you remove circularities, and we'll call that well-founded type theories. There is a lot to digest here, and I think we understand all these steps. But it's impossible for me to do this in 1 hour. So my goal really is to sort of give you an idea of the sort of things you need to pay attention to, and maybe just present what the problems are. So I think that I would be quite happy if I succeed in doing that. I don't see chat, so just a second. I want to make sure that I see chat. It's gone. Okay, but still I should see chat. There we go, I see chat now. Now, once you do this, you want to know, how do I know I got the right thing out of this? How do I know that the result is worth anything? Okay, so then you want to have some sort of results after that that will tell us that the thing we're doing makes sense. So what are some possible results? For instance, people keep proving the same kind of meta-theorems about their type theories. So for instance, we should be able to sort of close once and for all some standard meta-theorems for the type theories that we're going to define. So that will also tell us that our definition behaves well, because we'll put it to the test when we try to prove the meta-theorems. So another one would be that there should be a wealth of examples, of course. We should study what kind of type theories that occur in nature have you actually captured by doing this. And a third one might be semantics, of course, but that's a whole different, I mean, that's a lot to ask for. So if our general notion of type theory is good, then it should also have good semantics. And another one is implementation. You could actually say, okay, there's definitely a type theory. You have a general idea of what type theories are. Can you implement them in general? I will just focus on trying to explain this part here today. what is the definition? So the definition. And then I will say a little bit about meta-theorems, and I will try to give you an idea of what sort of examples we can capture. So I can actually tell you this first so that you will know where we're heading, okay? So what sort of examples can we capture? We can capture the sort of type theories that, okay, I'm gonna say this, are of the Martin-Löw kind. So I suppose you could say this would be Martin-Löwian type theories. So what does that mean? That means that we're going to have 4 judgment forms, the standard judgment forms of Martin-Löw's type theory. So these are that something is a type, that a term has a type, that 2 types are equal, and that 2 terms are equal at a type. So those would be the standard judgment forms. No strange things involving intervals. You can't have any subscripts or subscripts here on the turnstile. So of course, these are in principle, you allow hypothetical judgments. So there are contexts, and the contexts are supposed to be what, the name I would use here is intuitionistic contexts. So standard contexts where no linearity conditions, how you access variables, you can't split the context into 2 parts, there can't be anything special. So this is the scope we're shooting for. So this is going to include things like, okay, so of course, Martin-Löw type theory and variance, variance. And then something like calculus of inductive constructions, I think, would it fit? Yeah, it should fit. If you do it right, probably. Okay, let's put it like this. Something like hot book type theory, with the warning that you need to do universes in a slightly different way. Because Russell universes would not be supported by this kind of thing. Why? Because a Russell universes, when you have Russell universes, a universe is both a type and a term. But here we're going to have a strict distinction between them. So what would be, so these would be some examples. What would be some counter examples? So counter examples would be cubical type theory, for instance, because it wants to treat some types in a special way, intervals, or any of, like, you open some French papers and then they do things where they, if you want to have something like this, and then you have a linear context, that's bad. You can't do that sort of thing. So that sort of thing is out. But still, I think this is a good chunk here. Okay, now let's try to go through some of these steps here and sort of give an outline. It's way too much to do it in 1 hour or in the remaining time. So I'm just going to try to pick some points of interest here. Okay, so first of all, I'm just going to say this. It's a good idea, mathematically speaking, it's a good idea to use families a lot when you do this, as opposed to sets. For instance, to give you an idea, suppose you say that a type theory is a set of inference rules. Now, that's not really that's probably not what you mean. You mean to say it's a family of rules. Why? Because you're going to give each rule a name. And so to give each rule a name, that just means it's a family indexed by some indices called names. This will also allow you to have the same rule twice if you really want to have it. That may or may not be important. And so there are a bunch of other places like that where you need to be a little bit careful. I'm not going to go into details about well-founded trees and what does it mean to have an inductive definition. I'm just hoping that this is somewhat familiar, how to make inductive definitions, say how to inductively generate all expressions for a given signature. I will be specific about signatures, but nevertheless, how to define them. Okay, so we do want to say a little. I do want to say a little bit about syntax here. So let me say something about syntax. Okay, so dependent type theory is complicated by the fact that there are constructors that bind variables, lambda, pi, sigma, and so we need to deal with with binding structures. We also need to deal with contexts, and so the first thing that you always have to explain somehow is what are you doing about free and bound variables? So what about free and bound variables? And we could just pick some standard way like De Bruijn indices or locally nameless syntax or one of the standard approaches. And I think it's good enough for the purposes of this talk to just imagine that we're doing say De Bruijn indices. The thing that is maybe worth stressing is that we're going to we really want to stratify things so that we first talk about just bare syntax without thinking about types and so on. So for instance, to give you an idea of how this goes is, so here free and bound in, here I'm just going to say pick some standard way for the purposes of this talk, although we know how to do it slightly more generally, but I really don't want to get into that. Pick some standard way. Yeah, for instance, De Bruijn indices. Okay. But to give you this idea of how we're going to layer things, so let's consider context for a moment. So when people say, "Oh, you know, what is a context?" they have something like this in mind. They say, "Oh, it's a list. It's a list of variables with types. That's what a context is." And then they have well-formatness conditions and so on. So if you strip this down to its bare essentials, then the bare essentials, if you forget about types, the bare essentials is, oh, we just have some variables. But really, you can think of these variables as slots. So for instance, you could say, aha, so a context, one aspect of a context is that this is a bunch of slots. And these slots have certain names. And right now, we don't really need to know what goes inside, what goes in these slots. Later on, we're going to say, oh, yeah, types of some sort. But in the first instance, you just want to say, oh, it's a bunch of slots and they have names. And then I can put things in these slots. And so what we call this is a shape. So this is usually written as gamma. And so then a shape in general, I might write as little gamma. And so little gamma has a set of, so these slots, I'm going to call them positions. So positions. And the positions really are, well, these variables, right? So this one here has positions x1, x2, and so on. And if you use De Bruijn indices, then you would just say the positions are maybe just natural numbers. And so you would have, I don't know, suddenly starting to count from 0. So you could just say, well, they're just like that, okay? And so then for De Bruijn indices, a gamma would be just a natural number, right? And then its positions would be all the numbers less than it or something. So that's the sort of thing that you can do at the beginning, and that allows you to consider shapes in general. So I might say that I have a shape which prescribes some names of slots or positions, and that's all I need. I don't need to worry about whether these slots are variables or what they are. So that's the sort of thing you want to do in raw syntax. And then once you have that, let's try to attack the next thing. So where are we going with this? Okay, so at the end of the day, I want to describe, for instance, I have a type theory. I want to say, oh, my type theory is going to have pi, sigma, and lambda. Okay, fine. So clearly, I'm introducing three symbols called pi, lambda, and sigma. But then I need to say something about them. What is it that I say about them? So we would want to have something called a signature. Okay. So what is the signature? What should it do? It should describe the symbols of my type theory, and which means, okay, obviously list them. So something like, oh yeah, the symbols of my type theory are, and I'm just always going to use pi and lambda, and so pi, lambda, and say application. But there could be many others. But then what do you have to say about each one of them? Well, you have to say something. So notice that each one of them is going to it's either going, when you use it to build an expression, it'll either give you a term expression or a type expression. So each one of them is of a certain syntactic class, okay? So it has a syntactic class. Say this one has the syntactic class type, and I'm going to abbreviate it like this. This one would have the syntactic class term, because it would give me, when I use it, I will get a term, and this one would also produce a term. So there are two syntactic classes. Type and term. But then I'm not done. I also have to describe the arity. So there needs to be something that tells me what the arguments are. So I also want the arity here. What is an arity? In ordinary algebra, an arity is just the number of arguments that you want, right? So plus has arity 2. The unit has arity 0, and so on. It's more complicated here because in addition to specifying how many arguments pi takes, so pi is going to take 2 arguments, but I'm not done. I also have to explain for each one of them, I have to explain, is it a term or is it a type? So when I take a term, because I have 2 syntactic classes, so I'm going to say pi takes 2 arguments, but each one of them, now, okay, let's see. So the first one, let's imagine what this is going to be like. It's going to be something like pi, and then when we apply it, we'll apply it to 2 things, and one of them is going to be, say, A, and the other one is going to be B, and I'm not very sure about about this one, because I know that it's supposed to bind some variables. So now I want to say, okay, the first one is going to be a type. This is going to be a type. And it doesn't bind anything. So I would say it binds 0 arguments. And the second one, this one is also supposed to be a type, or a type expression to be precise. But now this one binds 1 argument. So I would say it binds 1. It's going to have 1 bound variable. That's the sort of information that I need to describe. And so that's what an arity would be here. That's what an arity is. Arity. Let's try another one. I'm going to do them by example because I give you the general definition. I think it's not going to be so nice. So a lambda. Now, everything in our syntax is going to be very explicitly typed, very explicit. So a lambda, you might think, oh yeah, this is a good lambda here if I just write like this. This is not enough information. We're going to require a lot of information. We're going to require that you always specify a lambda is going to take the type of X, the codomain, and the argument. So it's going to take, let's try to write down. Okay, so first you want, let me write it. So I'm going to ask that it's written like this. So lambda A. So here, there needs to be something. Let me call it B. And then I'm a little bit hazy on this because I know that something is getting bound here. And then there is an E and something is getting bound here. So I want to say, aha, it takes a type, which is the domain. It takes a type, which is now dependent over this, but I'm not really connecting that up. I'm just saying here, 1 variable will get bound. and I'm taking a term, and one variable will get bound. So here I would say the first argument is a type, not binding anything. The second argument is a type, we're going to bind one thing. The third element, the third argument is a term, and we're going to bind one thing. There's no type information at this point, it's just binding information. An app is even worse. App takes this information, so A and B, the same information about types, everything has to be fully tagged, and it may be, and then it needs to take two arguments. So now this one would be, okay, repeat all of this. So it takes a type, it takes another type, but this other type will have one bound variable here. We will bind one of these variables because we have a dependency here. And then, oh, and these two are now not dependent on anything. So, and then we take two terms. Not dependent, the zeros are not dependent. Okay, so that's what a signature is going to be. It's going to be a family. So what is a signature? It's a family. Its indices are, these are called symbols. And each symbol is mapped to some information. Namely, so if I have a symbol S, it has a corresponding here. This is its class. So let me write it like this. It's its class, and it's either a term or a type. And then it has an arity here, this gadget here, which tells you how the arguments work. So I'll write that as alpha. And so it's a family, it's a mapping like this, from a bunch of symbols to this information. So that would be the first thing that we give. It's just raw syntax. As you see, no information about types, just how many arguments, how many variables are getting bound, is it a term or is it a type? Once you have that, you can start creating, you can start making expressions. And so I have something here. I can drop things in. So let me show you an example. What I wrote here, I had ready, so I could have done it like that. Too bad. Okay, so just a more readable version of that. But now we can maybe, let's see if we can understand the official definition of what is raw syntax. How do I move this thing like this? Okay, so the raw syntax over some signature sigma. So in general, I will use sigma, so that's a signature. Consists of what? Well, a collection of raw type expressions, and so expressions are, so these are expressions for the given sigma. Sigma tells me what symbols I can use, so what type symbols I can use, things like pi, sigma, plus, times, or maybe even constants like nat, over some shape gamma, which tells me the shape of the context that I'm in. And then there's a corresponding term for expressions, and these are generated inductively. So for every position in my shape, think of this as, this little thing is just like the information about the context, but still no types, just what are the available slots, what are the variables. So for each slot, I get a free variable, which I'm going to just call var I, okay? That's an expression. And whenever I have a symbol, S, then I can form S of E is the symbol applied to the correct arguments. And then I will get, well, either a term or a type. And what are the correct arguments? Okay, so for every argument of S, I need to give an expression of an appropriate type. And this is just a notation that says, okay, when you give the type, you can use whatever variables are available in the context. So these would be the free variables that you can mention. And then you can also mention the variables that will be bound in this position. Okay, so these will be the variables that are bound. And so you get a definition of raw syntax. Okay, any questions at this point? Okay, so now, assuming that we have some idea of how expressions might work, let's see what we might say about type theories, and I see I'm wildly running out of time here. So let's try to go through these levels of type theories. Okay, so there are three levels of type theories, and the last step, you will know everything about the last step if I tell you make sure circularities are removed. So circular references are removed. So I will comment on this if I have time a little later, but if I don't get there, the last one is not, conceptually speaking, is not that complicated. Just make sure everything is well founded. All the references, when you use, okay, one more sentence about this. For instance, the rules for lambda refer to pi. The rules for pi don't refer to any other symbols. So that's good. If the rules for pi referred back to lambda, that would be a circularity. Okay, so that's the sort of thing you want to avoid in the last step. And here, I'm going to speak now just about 3 and 4 to try to see where we get, how far we can get. Okay, so raw type theories. So in principle, a raw type theory, what's a type theory going to be? Okay, so T type theory, a raw type theory, raw because I haven't put any conditions on it yet. Raw type theory. It's going to be, well, a family of rules. Oh, okay, so first of all, it's going to be over some given signature. Because the signature tells us what kind of expressions we can write. What are the types, what type expressions and what term expressions can we write? And it's a family of rules. That would be like a family of rules. That will be our first approximation, but we have to explain what is a rule. So let's look at this. Okay, so what is a rule? Okay, everybody knows what a rule is, right? You just say, let's have a look at one of them. So you might say something like, okay, if A is a type and XA, B is a type, then, so in our notation, we would say something like pi A, and then maybe we say something like, you know, I want to say B here, but now I'm already getting, you know, then now already different people will use different notations. For instance, what do I mean by this? So maybe I want to write it like this instead. Or maybe I want to write gammas everywhere. Should I write gammas everywhere or should I not write gammas everywhere? What's the answer? Well, different books say different things. Some people say, oh, the gammas should be there, but we're just going to be sloppy. So we don't have any freedom to do that. We need to be completely precise about what it is that we're doing. So first of all, we're not just going to write gamma, gamma, gamma everywhere. Instead, what we're going to say is a rule. So we need to describe what a rule is quite precisely. And we're not going to say there's always just some random symbol gamma there. We want to, so it's not there. Next, what about this B? We want to somehow indicate that this B now here, that X may appear in it. And so this is the notation I want to use. And I will explain why I want to use this notation. But anyway, then here, down here, what do we say? Okay, so here you need to say something like pi A, you know, probably B or B of X, or so there needs to be some notation here. Okay, so I'm not entirely sure how this would work in concrete syntax, but anyway, the conclusion I want to get is that this is a type. So the first observation that is also kind of obvious is that, I think I don't like this, I want this to be still a little, is that, okay, so these things are called premises. And this is a conclusion. And clearly they take the shape of judgments, and I'm kind of skipping over what judgments are. So judgments are going to be the standard ones, and they may be in a context, so they would be called hypothetical judgments. But nevertheless, A rule is going to have two things. It's going to have a family of premises. So a rule R should have a family of premises which are hypothetical judgments, so they're judgments. And it should have a conclusion, which are, again, a judgment. Okay, that's fine. But in this particular rule, what is this A doing here? And what is this B doing here? What's the role of these two guys? What do I mean when I write this? What is A? So people say, well, it's something like a meta variable or something like that. So we need to be quite careful what this is. If we want rules themselves, you see, because we're defining, there is here an interesting question of levels. We're defining what type theories are. And we're going to say a type theory is a family of rules. So rules need to be object level entities, because otherwise I can't say it's a family of anything. So I need my rules to be real actual entities. So I see that a rule is going to be something like a pair of things, but I need to be quite careful about the A and the B. So I need to specify that, say, this rule gets to mention A and B and what they are. So these are meta variables. So a rule has to have a third thing here. It needs to have some information about meta variables. Such as this A and the B here. What is the info about the meta variables? What is it that I need to know? Well, I need to know that, so what do they look like? Actually, if you look locally at this rule, it actually looks like A is just a type constant, isn't it? And B looks like it's a type former. See, it looks like it's something that is going to form a type, and it takes one argument. So maybe we can look at another one. I have them here, a bunch of them, just to observe them. I'll just drop them in. Let me see. So I'm going to drop in a rule that may or may not be something that you like, just so that we can stare at it. And now I ruined everything. What happened? There's another one. Oh, it's just because it's really big. This number 6 here, like that. Ah, doesn't want to go there. My God. Okay, go away. I'll try another one. And oh, that's the one I just had. Okay, I can live with this one. So here's another rule. It's a rule for application. It may or may not be sensible, but at this level, it is going to look okay. So what does this one? This one say it has 1, 2, 3, 4, 5 premises, and it has a conclusion that says that this term here has type B of A. The premises are kind of weird because they, you see, have A here twice, and that's really strange. So maybe it's not the kind of rule we would want, but nevertheless, let's observe the meta variables. So there are, again, meta variables A, and there are meta variables here. Where are they? They are A, oops, no, let's hope this works. A, B, F, little a, right? Well, and then they repeat, okay? So these meta variables. And what is it that we want to know? Well, we want to know that A is something that forms a type. So it's going to be, it's going to give me a type, and it doesn't take any arguments. Whereas B, for instance, is going to form a type, but it wants one argument, which is a term, and it doesn't bind anything, of course, because it's just a meta variable. It's not an operator like pi. Whereas F, for instance, gives me a term, okay, and it looks like it doesn't want any arguments. So I would say, yeah, it doesn't want any arguments. And similarly, A is just like a term, and it doesn't want any arguments. But this, it looks like a little signature, you see. So what these A, B, F, and A are is really, what am I doing is I'm taking the signature and I'm extending it with some additional information, this additional information about the meta variables. I'm going to call, you see, this is extra info. So meta variables as symbols, which are then local to the rule. That's one way to do this, and that's how we want to do it. So this info about meta variables really is just a suitable extension of my signature. And once I have that, then I know what the rule is. And then I can read this definition. It makes sense, namely that it's over a signature and it's just a family of rules. The next thing that you need to figure out is what makes a rule good. And we have a definition of acceptability, and it's kind of nasty and complicated. But it is.
Can I ask a quick question?
Yeah, sure, of course, please do.
The premises that come before, do the premises after get to depend on them?
Let's say again.
Do the premises that come after the premises before, are they depending?
Okay, so you're asking, is there an order on these premises,
Yeah.
and do they depend on each other in any shape or form? At this level, I would say no. At this level, they don't depend on each other, and the raw part is just about listing the premises. The raw part is just what you need, the kind of information you need to verify that something is a derivation. But of course, later on, you would want to worry about this. For instance, here, if you look at here, how do you know that this thing is okay? Well, this thing is okay later on, not at this level, but later on you want to say this thing is okay because this is a good context. Why is this a good context? Well, this is a good context because A is a type. But how do I know that A is a type? Because I have a premise that came before that says that A is a type. But it can get worse. Like for instance here, how do I know this one is okay? They say, well, this one is okay because this pi A B var 0 is a type. But how do I know that? To know that, I will need to rely on a previous rule about pi. I need to know that A is a type here, and I need to know that B of var 0 is a type. Why is B of var 0 type? Well, because I have a premise. So I think you're asking about this kind of dependence. Is that the question? Yes, that's certainly something that you need to incorporate at some point, but maybe not at this raw level. But that's the next step that we want to do. So let me show you some variations of the rule. Let's try to, I will just give you an idea of what it is that you need to think about when you define what rules are acceptable. So why is this rule not acceptable? It's because it gives two types to A, you see? It's not acceptable. So let's try to find some other. Let me drop in some others. Here are some other variations of the app rule. So this one here is what you'd call the standard rule, okay? It's a nice one, and so this one looks okay. And notice the nice properties that it has. The premises are just, so to speak, typing the meta variables. There are 4 meta variables to this rule, A, B, F, A, and these premises are nicely telling you what each of the meta variables is. This one is a type. This one is a type, which depends on one thing. This one F is a term, doesn't depend on anything, but it has this type. This one is A, it has that type. So that's a good rule. It's going to take care of the meta variables, each meta variable exactly once, not like this guy here, okay? And then the conclusion also needs to be suitably reasonable. How about this rule? Is there anything wrong with it? Well, no, I don't think there's anything wrong with it. It's a bit strange because it says that F has type A here and A has type A. But it looks okay, right? So maybe it's not a very useful one, but it looks okay. How about this one? This one, we'll have to stare at it long enough to discover what's wrong with this one. Can we tell? Is it good or bad? So, okay, so what we want is each meta variable receives one type, A, B, F, A. They need to have the correct thing because this extension here, when I extend my when I extend my signature, I will say this information here is forcing me to say, to make sure that A is a type, make sure that B is a type, but it has to have been a context with one thing, and so on. And so
we can't use substitutions for B of A in the conclusion.
You can't form B of A is, what is wrong with B of A?
Little a has a pi type, whereas the B expects it to be a
okay,
family
yes.
of A.
So this one would be suspect because something doesn't fit. So what is it that doesn't fit? This B says here that this thing, its argument wants to be of type A, but little a doesn't have type big A. So whether or not this is well formed will depend on whether this type theory can prove that A equals, so this would be okay only if the type theory can also prove that A equals this thing. Otherwise, it's not good. Okay? So a bunch of conditions like that. I'm running out of time. So a bunch of conditions like that to define what it means to have an acceptable type theory, then remove the cycles, then try to prove some meta-theorems. So what are the meta-theorems would you want to prove? So meta-theorems like uniqueness of typing. So let me just give you one because it's as the time. So the kind of meta-theorem that you want to prove is like this. Suppose my type theory shows that A is a type, and suppose it shows that B is a type, and that T has type A, and that T has type B. From all of this, also that it shows that A and B are equal. So that would be called uniqueness of typing. And other theorems like elimination of substitution, things like that. So there's lots and lots of this here. I'm going to stop here, and I'd rather have the discussion drive the rest of the seminar than me yapping on. So I'm going to stop here and hope that there are some questions.
All right, thanks a lot, Andrej. I'm going to say we used to do applause one way or another in the past, but we're not going to do it. It's not because we don't appreciate the talk. We always appreciate the talk. The point is it messed up a lot of mics for a lot of people. So from this point on, we will just be letting our speakers know how much we appreciate them.
You can have visual applause. You don't have to have it for me, but next. Yeah.
But yeah, so it's not you, it's our microphones.
Okay. So there is a question.
You can see visually that people are muted and are applauding, which is great. But anyway, I'm going to open the floor to questions. So if you have a question, unmute your microphone. Don't applaud, just express orally how much you enjoyed the talk and ask the question or make a comment.
Okay, so I'm not sure I want to hear whether you enjoyed the talk, but nevertheless, there is a question when it says, why do you say a family of hypotheses? Are you restricting its size to be finite? So for the most part of everything that I talked about, we express everything using just always saying family. So for instance, a signature is a family of symbols with some information. The premises of a rule are a family. For the most part, there is no size restriction on these families, and you could do infinitary. As far as we can tell, everything goes through with infinitary syntax, infinitary rules, and so on, infinitary signatures, no restriction anywhere. The restrictions are going to come in, the size restrictions will come in maybe later when you want to actually implement it, or if you need the finitary character of your theory or countability for some purposes. So, okay, that was already a question there, but now, does anybody have any questions?
I may as well ask a question. Could you scroll up a bit to the example of a rule, number 5, I think it was labeled. Yeah, there we go. Could you say just a little bit about the types that appear in the context of the premises, like the 0:A? What sort of restrictions do you put on, or what sort of things are those?
Okay, so this will go in levels. So the raw level is going to say these types that appear in context, like this one here, it needs to be like this one. It will just say it needs to be a raw type expression. I don't care what it is, just a raw type expression. Okay. But there will be a question of what variables may appear here. Yes, because what will be? Let me do this in a more general form. So in general, we're going to say here, I have some context gamma, and then I have some judgment here. What is this context gamma? Well, this context gamma has a certain shape of slots. This tells me which free variables I may mention, and then for each position of gamma. So if I is a position in gamma, so then gamma I needs to be something. So the corresponding type. So this here, if this is my context gamma, this A is gamma 0. So gamma I needs to be an expression. So at the raw level, an expression, it needs to be a type expression. It needs to be over my ambient signature sigma, extended with whatever meta variables this rule allows. And what free variables can it mention? The answer is all of them. So in particular, at this level, I would allow here something like 0 is a free variable of type b of var 0. And that would be considered okay at the raw level. So you can have cycles inside the context. I'm not trying to well order the context, that comes later. And what is interesting is that this doesn't actually prevent you from using such cyclic contexts. You can use them. It's just that it may be difficult to form them or something, but you know, they seem to be okay. Is that what you're asking about?
Yes, thanks. And then later on, you put in a restriction like that when you do the acceptability or the well-foundedness.
Right. When you do well-foundedness, you would say, okay, but you know the contexts need to have some well-founded order on them so that I can tell that they were built in some reasonable fashion. And the same goes actually for rules, right? Usually there is a very clear order to rules. First you give the rules for pi, then you give the rules for lambda and application. And when you give anytime you give the next rule, you are allowed to mention things that came previously, and there is usually an evident order. But in principle, you can come up with examples where you don't have such an order. So here's a bizarre way of stating that you have universes. You would say, how does that one go with the universes? You say, we have, if you give me the code, there is a type. Okay, so I'm going to say, what am I going to say? I'm going to say something strange, but it kind of makes sense. Okay, so I'm going to first say there is U, a constant U, which is an element of the type LU. So that's one rule. And the other rule will be that if I have any element A of what? Of L. It's here. No, it's not. Maybe I should. Do you remember, Philip, how we do it? Peter, help us. We want to have type.
Everything you've written looks good to me. I think that.
How do I finish it off here? So I want to say
A is an L of U, and then on the bottom.
Oh, yeah, there we go.
Yes. Then L of A is a type.
L of A is a type. Okay. So what you do here is you think of U is the code of the universe. L decodes codes to types. So these two are cyclic, but they make sense. Okay, so U is an element of the. It's an example of type in type. So you could I think you could probably stratify these, but it's an example of type in type, and it says, okay, you use a code of something. Okay, it lives in a universe, and so if you try to make sense of these two, then it gets weird. For instance, how do you know that this is a type? Why is this a type? Derive that this is a type. That would be derive the presupposition that this is a type. Well, we can derive the presupposition that this is a type using this rule. We just stick in U here, right? But then we get ULU, and we say, oh, we're done by this rule. So these two rules are cyclic, and it's a kind of weird circularity that you may or may not want to have.
And if I can just mention another twist on this, if you give annotations on those so that UI is an element of UI plus 1, where I is an external natural number index parameter, so you've got nat many symbols UI, so UI is an element of UI plus 1, and then the rule on the right says, again, you copy that out with the annotations. Now, this is no longer cyclic, but it is non-well-founded if you try to justify which rules depend on each other's. But again, you can get off the ground to do derivations with it perfectly happily.
Like this?
Yes. Yeah. So your derivations are well-founded. You can use this perfectly well. But if you try and order what rules depend on what here, then it's non-well-founded because they keep going up and up and up to depend on each other.
I have another question. Can you hear me?
Go ahead.
You mentioned an equality of some sorts. I'm guessing is judgmental equality, but you didn't mention it in much detail. I remember that when you add a judgmental equality, you have to make sure all your symbols kind of respect it. How do you handle that?
Can you be a little more, like, give me an example of what you mean by respected?
So if you have pi types over some type family and those are judgmentally equal or something.
Okay, so let me try to give you a simpler example, and you tell me if that's the one. Suppose I had a type former of lists, which says if A is a type, then list A is also a type. So lists. Then you would expect the following to hold. If A equals B, then you would expect that list of A equals list of B. Is that what you mean by respect?
Yep.
Okay.
But there's also a few more that you need to do, and it gets a bit difficult with binding as well. So I'm interested.
Yeah, with binding it gets nastier. That's why I wanted to write this one down. With binding, you're going to have, so yes, so maybe that's a point that's worth, let's try to write it for pi. I think the pi type will show you what's going on. So for the pi type, you would want to say what? You would want to say, suppose A1 equals A2. So I can tell what, I can show what, I know what conclusion I want. The conclusion I want is pi, let me write this in a traditional notation here now. Pi x A1 B1 of x should be equal to pi x2 A2 B2 of x2, and let's be careful, let's have x1, x2 so that we don't accidentally do this. So under what conditions? Well, the conditions would presumably be A1 equals A2, and here I'm going to get into trouble, right? Because here I'll write something like x1 of type A1, and in this context now B1 of x has to be equal to what? Well, can I write B2 of x? Here, B2 of x1. Here I write B2 of x1. Can I do that? And there's a question about this because I need to worry about whether this is well formed. And yeah, that's the sort of thing you need to address and be careful about it.
So that's actually exactly what the clauses in acceptability.
Yes. So one of the clauses in, so what this really is, this is a congruence rule. a congruence rule says that a symbol, either a type symbol or a term symbol, respects equality. And so it is what we call a structural rule. Maybe we call it a structural, but we definitely know. We want, so one of the acceptability conditions is that these kinds of things have to hold. The congruence rules have to hold, and you're completely right. When you have binding, you need to think carefully about what the congruence rule is, because this one is at least a little bit tricky because of this point here that B2 is something. See, let's be a little more specific here. What are the premises here? There are some presumably you want to know that A1 is a type, and you want to know that A2 is a type, and now you want to know that B1x1 is a type, and you want to know that in the context A2, B2x2 is a type, right? So these would be some sort of additional assumptions here. And now you stare at this and you say, why is this a type? I don't really know that this is a type, because what I do know is that B2x2 is a type, right? There's some trickery involved. This is, I think, is the trickery that you are referring to. And one has to deal with this and make sure that it's okay, that I'm not doing anything bad.
May I add something?
Sure.
So there's kind of two different approaches you can give here as well that we consider both of. One of them is you say that the user has to supply all of the rules, sort of the structural rules and the logical rules and these congruence rules as well. Or you can say the user should only give the logical rules and the rest are thrown in automatically, the structural rules and then these congruence rules. And with the structural rules, we take a view of always throwing them in automatically. And then for the congruence rules, we look at the difference between the two versions. Either you ask, did the user throw them in, or the user could have thrown some alternative version in, so long as they prove the versions one that we say you expect you should have. Or you can say the user just throws it in the logical rules and the specification, and then you automatically convert them into congruence rules. And as long as the logical rules are well enough formed, you can always convert them, and it works.
Once you see, so you can ask, where will the congruence rules come from? Once you see the rule for pi, you know what its congruence rule will be. So you can generate it. And then you can ask, is it derivable, or am I just throwing it in, or is every instance of it true, or what's going on?
Can I ask another question?
Yes.
Going back to the examples you gave with the symbols with their arities, they all have one bound variable. What happens, for example, if you have multiple arguments and they all depend on kind of the same bound variable? Is it the same bound variable, or is it bound in each argument?
Okay, so application, I think, is of this form. No, sorry, lambda will be of this form. Let's stare at lambda. So the lambda says, I take 3 arguments. So let's have have an example. So it's going to be something like lambda has 3 arguments. The first argument is just some type. Let's say it's like natural numbers. The second argument is going to be a type, but with one bound variable. So let me indicate it in some random fashion. I'm going to say x, and here is a type. Say something like, I don't know. So it's going to be like some type. What's a good type to be dependent on natural numbers? Vectors of dimension x plus. Okay. So that would be the next one. So this is a type. It says it has to be a type, doesn't bind anything. This one binds something. It binds an x, and then it's a type. And this one also binds something, y, and then here it does, like, it's something like, you know, the 0 vector of size x plus 7. And now this is not going to, because this one says x plus 3 and this one says x plus 7, but syntactically this is correct. And I think what you're asking is, what is going on here? Because, okay, we're binding one variable here, we're binding one variable here. Is it the same variable? What is its type? What is the question?
Do you mean y plus 7 or x plus 7?
Yeah, we wouldn't be allowed
Sorry.
to write that.
And y, here I meant y. Y plus 7. Okay, yes? So at the syntactic level, there is no, let's ask, okay, so let's ask this. So as far as just raw syntax is concerned, it only cares about what variable is bound in what expression. So here there is no relation. Here there is nothing that tells you that x has anything to do with this nat. And there is nothing that tells you that this y has anything to do with the nat. That information will be revealed when you look at the rule for lambda. When you look at the rule for lambda, there you will see that this x is supposed to have a type nat. Why is that? Because the rule for lambda, and now I'm running out of space here, is going to say, the usual rule for lambda will reveal that, because it's going to say, aha, if you have a type A, and then you have x of type A, and then you have b of x, which is a type, and you have y of type A, and then you have e of x, which is a type, a term of some type. So which type in particular I want? I want probably b of y here. Then lambda applied to A, x, b, x, y. I'm just making up some random notation here for bound variables. Y, e, and this should be a y. E, y has type pi, A, z, z, b of z, say, like that. So now I know, only after I see the rule do I know that this variable here is binding there, is bound to this, okay? But it could be something weird. For instance, this one here, it could say something strange. It could say here A cross A, for instance. And this one maybe could say list A. And that would be a rule. It would be a really weird rule, but it would be a rule.
And to add something else, so one aspect of what Ali asked was, are they the same x, so sort of the same bound variable in each?
Ah, yes.
That's not even a question one can ask unless one's using named variables. It's if you're using de Bruijn indices, then you can't even sort of, all bound variables are the same, or no bound variables are the same. And so in the version of this where we say we're just using de Bruijn indices, then it's a question that doesn't quite make sense. As Andrej mentioned, we have a slightly more general framework that we abstract to where named variables could be an instance, so one could ask it. But since we're always using it to the interface of the general framework, nothing about the general setup can be affected by that question, even though then you can instantiate it afterwards with named variable where it's a question that makes sense. The general framework can't access that. It's hidden by the interface that we use for the variable binding.
All right, we're almost at the end of our time, one way or another, but maybe one more quick question.
Yeah, I have a question. So some of the point of this is to prove, so that meta-theoretically settle the stuff that's being reproven over and over and prove it meta-theoretically. So I'm wondering, what are you able to prove, and is there something you would like to prove that you aren't able to prove?
Mm-hmm. Okay, so the theorems that we have so far are elimination of substitution, derivability of presuppositions. So substitution elimination just says if you have a derivation that uses substitutions, you can then derive the same thing without substitutions. The derivability of presuppositions says that if your theory has this is part of it being acceptable. If it has this a certain property, then it always derives presuppositions. Presuppositions means a thing like, just to give you an example quickly. So a presupposition would be this. Suppose I derive from gamma that T has type A. Well, a presupposition of this is, for this to make any sense, is that first of all, A is a type. Otherwise, it's really weird. And so the presupposition theorem says if you have some derivation of this, then you can actually also get some derivation of that. Okay, so that's another one. That's just a basic theorem that says that it's, it's not all messed up. Uniqueness of typing I already talked about. Peter, do we have any others? We have certain inversion principles. So another one would be inversions. That tell you that as far as that's possible, you can put derivations in at least somewhat canonical form. For instance, this would be something like this. Suppose I have a derivation, suppose I have a derivation that shows that pi AB is a type. Can I then show that there is a derivation of the same judgment where the last rule that is used is formation of pi? So pi intro. And then some other derivations up here. Sorry, this is acting up. D prime, D double prime. So if I have a derivation of this, can I have a derivation that is of this form? So that's kind of an inversion principle, and we have those as well. Are there any theorems that we want to prove but don't know how to prove? I don't know, Peter, do we have any?
I think there's none that we want to and don't know how to, but there certainly are ones that we want to and haven't finished setting up the framework to kind of to do the details. We have the idea of how we do them, but we haven't done them.
Yes, yes.
And the two big ones there would be to define the semantics and give the initiality for the semantics. And then on the other hand, to define the logical framework embedding and give the conservativity of the logical framework embedding.
Okay, so Peter's going immediately for the big theorems. I was thinking of small theorems like this, but yeah, those would definitely.
Since Ali's asking what we want to prove, then.
Yeah.
Thank you.
All right, I think we're almost at the very end. So
One more question.
that has to be a quick one.
It has to be a quick one. Okay, how general is this framework? I might have missed it at the beginning, but for example, does it take in, there's a lot of things people would call type theories.
Yes.
Does it encompass all of these?
Okay, so
you can't encompass?
Okay, so as a general rule, if you have any kind of judgment that isn't standard, so the standard judgments are something is a type, something is a term, two types are equal, two terms are equal. If you introduce a fifth kind of judgment, or you fiddle with any one of these, then it's out of the scope. Of course, certain extensions will be easy to see. It will be easy to see that we can deal with certain extensions. But and then another kind, so that's one restriction, is you have to stick to these four judgment forms. And contexts need to be intuitionistic. So this means that the variables, there is no restriction on how you access variables in the context. No, like linearity or anything like that. It shouldn't, nothing like that. The context cannot be split into two parts when one part is special. Nothing like that. All types have to be treated equally. It cannot be the case that some types are special, like are not fibered or are fibered. I'm not saying that sometime in the future, maybe, clearly there will be possibilities to extend what we're doing, but we need to get this done first in this well-defined way.
Maybe to sort of summarize that briefly, it's just we fix the judgment forms and the structural rules, keep those fixed, and then everything else after that can vary. Sorry, Chris. Sorry.
Yep.
Oh, on behalf of Ali, I'm going to say that he's extremely satisfied with this answer and there are no follow-up questions. I'm going to reiterate that we thank Andrej a lot for a great talk. And that's it for today. We're going to meet again in 2 weeks with Anders Merdberg speaking on something. And next week, tune in for the democratic debate. It will be very sad, but yeah, that's your entertainment instead of hottest. Okay, thanks a lot, everyone.
Thanks, everybody, for listening. Goodbye. We should have a visual goodbye.